Good morning. This lesson is for my Honors Integrated 1. Before I get started though, I want to say I hope everyone is doing okay out there. This lesson is for section 3.4 in our book, and let's just go ahead and get started. We have 3 goals for this 3.4 lesson. Our first goal is to define a relation, a domain and range. The domain and range, sorry, not a domain, the domain and range. Our second goal is to understand ways to represent relations. And our third goal is going to be to define functions. So let's just jump right in. It's a pretty simple lesson. A rule of thumb, if I write it, you write it. So anything on the board you want to write. Also make sure to add some little notes for yourself, because again, this is our book and we want to make sure that if we ever have to come back and look at something, we're able to tell ourselves in the future what this concept was and be able to use these notes as a resource. So let's make sure if I write it, you write it. And so our first goal is to talk about what a relation is. A relation is a set of ordered pairs. I wasn't until I was in college that I understood what ordered pairs actually were. And in mathematics, they're very good at picking names for things that actually describe what they are. And they're called ordered pairs because they're ordered like the alphabet, X, Y. So that's what a relation is. I'm going to wait a little bit to talk about what domain and range are as I work through the ways to represent relations. Now, we've seen domain and range. Domain are the set of inputs, range are the set of outputs that was mentioned in the last lesson. But we'll see a little bit more with this. I actually wrote that on the board. Okay, there we go. Okay, so our second goal is to show ways to represent relations. So obviously I can represent a relation as ordered pairs. Remember, it's a set of ordered pairs. In the definition, I gave you 1 ordered pair. In the examples I'm giving you 2, there can be infinitely many. All right. So obviously I can represent relations as ordered pairs. Now, ordered pairs you can represent graphically, right? And so I will put the coordinates to these ordered pairs, but you see I have the input of A that gives me the output of B. The input of C gives me the output of D. So these actually represent the ordered pairs. So you're going to be expected to be able to go from one to the other. So if I give you a graph, you should be able to make the ordered pairs. If I give you the ordered pairs, you should be able to graph them. You want to bounce back and forth between different representations. And that's very important in math because maybe something's not so apparent in one form, but in another form it is more apparent. So this is why there's multiple ways to represent a concept. The third way that we can represent a relation is a table. And so tables have X values and Y values, or input values and output values. So the input value of A gives me the output value of B. The input value of C gives me the output value of D. And again, this is just another way to represent an ordered pair, right? So I just put the parentheses around in the comma. There's your ordered pair. Now, we are going to use tables to help us find patterns in the next lesson. And so I do like to stress this form of a relation. Our last form of a relation is a mapping diagram, and this is probably the first time you've seen this. All of our inputs go in one box, all of the outputs go in the other box, and these arrows show us who they go to. So here I know that if I plug in A, I get B. If I plug in C, I get D. So here this is saying that A goes to B and C goes to D. All right. And I wanted to, again, wait to talk about an example of domain and range before I check off that box. And so in all of these examples, we would say that the domain or the input values are A and C. And the range, or all the output values, are going to be B and D. Okay, so it's pretty simple to find this, and looking at the domain and range of this example, I'm going to conclude that these examples must be discrete, and if I look at the graph, it is discrete, it's individual point values. So I'm going to end the part one of this two-part video because I have defined relation, domain, and range and ways to represent relations, and I want to make something very clear. If I give you this, you should be able to write these three from this. If I give you the table, you should be able to write ordered pairs, graph them, and write them as a mapping diagram. You need to be able to turn one version into the other three. So that's the end of the first part. All right, we're moving on to now part two of our 3.4 lesson, and I'm going to define relations. And sorry about the interruption, I must have just received an email. So our third goal is to define functions. A function is a relation where each input only has one output. So I wrote two examples on the board. I set up situations to represent each relation in its three other forms, and I'm going to make observations about each. For the sake of time, I've picked very specific examples to show something. You'll see in each. So let's go ahead and look at our first set of ordered pairs and determine if this is a function or not. So my first set of ordered pairs, I have an input 2 and it goes to the output 3. I have an input 3, it goes to the output 6. I have an input 5 and it goes to the output 6. Does each input only have one output? And the answer is yes. Each input only has one output. I have the input of 2 once. I have the input of 3 once. I have the input of 5 once. So each input has one output. Now, notice that I have a repeating output. Nowhere in this rule does it say that each input can have a unique output. So this technically is a function even though the outputs are repeating. That is allowed in this definition. And so when we're talking about, for example, laws that are created, you can't break a law that's created if that law doesn't specifically, outline or define, for example, repeating outputs. So since this is still technically obeying this rule, this is a function, and so I just want you to see what this specific function looks like. And again, I picked very specific examples, and with this example, I wanted to talk about it because this one is important because it has a repeated output. Okay, so graphically, it's going to look like this: 2, 3, 3, 6, and 5, 6. So this graph is a function. It can be horizontal. That just shows me that I have a repeated output. So the horizontal shows me that I have a repeated output. If I'm going to make it as a mapping diagram, I'm going to write all my inputs 2, 3, 5, and then I'm going to write all my outputs 3, 6, and 6. Now, it's very common not to repeat an input or an output, so we're going to write it like this. Okay, so I know that 2 goes to 3. I know that 3 goes to 6. And I know that 5 also goes to 6. But again, you're not wrong if you put the second 6 down there. It's just that we tend to see it written once. And finally, I'll write it as a table. 2 goes to 3. 3 goes to 6. I gotta learn my numbers. And 5 goes to 6. And again, it's okay if the output repeats. So This was a very specific example that I wanted to point out about a repeated output, but that's still technically a function because each input has a unique output. All right, so let's look at the second example here. The input 1 makes the output 4, the input 2 makes the output 3, and the input 1 makes the output 2. Here I have repeated inputs, and they're going to different outputs. So this, right now, by definition, is not a function because I have the same input going to two unique outputs. And I want to point out how that looks in these other forms. So 1, 4, 2, 3, and 1, 2. I want to point something out about the position of these points. This point is vertical to this point. They're vertical. And I'm sure you've heard something called the vertical line test. And the vertical line test says that if I can draw a vertical line through my graph and it hits more than one point, it's not a function. And so this graph fails by the vertical line test. And the vertical line test is just a way to show that I have repeating inputs. So this fails by the vertical line test. Now, you might be asked to determine if something like this is a function. And so all you need to think about is if you draw a bunch of vertical lines, how many times does it hit the graph? And it hits it each time once. And so what that would mean is I don't have any repeating outputs. So again, if I have repeating inputs, if I have repeating inputs, that means I can draw a vertical line through multiple points. So if your graph looked like, let's say, this, and I drew a vertical line through it, you would see that I'm hitting the graph twice. And so that tells me that I have repeating inputs. Remember, these are x values, and if they repeat, you're going to see one point on top of the other. So this is not a function. Again, it fails because I have one input going to two outputs. That's what the vertical line test shows. Again, we don't like to repeat values, so I'm going to write my inputs as 1 and 2, and my outputs as 4, 3, and 2. It doesn't matter what order you put them in, to be honest, but 1 goes to 4, 2 goes to 3, and 1 goes to 2. Kind of a jumbled mess, but you can see that the input 1 has two outputs, and therefore, again, it fails the definition of a function. This is a relation, right? All functions are relations, but not all relations are functions. I had to think about when I said that because I often trip myself up on that. And then let me write this as a table and make one last observation about this. So 1 goes to 4, 2 goes to 3, and 1 goes to 2. And so here I see that I have repeating inputs. And that tells me again that I do not have a function. So repeating inputs are bad. That means that your relation is not a function. If you can draw a vertical line through more than one point, it's not a function because it fails the vertical line test. But again, the vertical line test shows repeating inputs. If I have a mapping diagram and two arrows are coming from an input value, it's not a function. So hopefully this clarifies everything. Again, I wanted to just be very specific with the examples on this one. Some of your problems won't have repeating inputs and repeating outputs, and you just, again, have to ask yourself, does it follow this definition where each input has one output? So hopefully this makes sense for you guys. I'll see you later. Have a good day.